Okay, let me show to you what's exactly going on. This is kept happening from early morning. And I thought it's just temporary, but it keeps happening because I don't have the questions in the module. I have them in front of me. I'm trying to copy them to the module. And when I finish, it takes me like 5 minutes to just type one quiz. By the end, when I save it, it closes. And I wasted 5 minutes. I retry again, copy the quiz. I wrote them in a Word document, just copying them. And when I try to save it, it says that there is a problem. And the same error message I sent you, that's the one I kept receiving all the time. So maybe I show you here. Let's say I try to make a quiz, multiple choice question. My name is, oh, oh, let, oh, or let me show you some S waves, wave, S wave is generated, wave generates E wave at interfaces, U2. This is a question, it's a legal question, it's a correct question. Let me change this thing. Due to mode conversion, that's the right answer. Mode conversion at oblique angle. I choose this one as the correct. Let me try another question. Uh, Normal. It's just that's the wrong one, obviously. Velocity change due to density change. This is an arbitrary answer. Waveform expansion due to the source. Let me see what happens. This time it worked. Anyway, we'll just continue with what we kept because I think.
Mr.
Yes,
I have a question from the previous lecture.
go ahead.
Why we don't use the reflected ray to estimate the layer thickness? In
Okay.
slide 22, you didn't answer it.
Which slide you mean?
22.
Why we don't use? We can use actually. In this case, we can use,
No,
but
the reflected ray.
reflected, you mean?
Yes.
The blue one. That's a good question. The question is why we don't use the reflected energy to estimate the depth to layers. Because they're going to be much easier and you can easily know them. It's just 2h over time. 2h over time. That's the distance. The simple answer, because they are not the first to arrive. So if I go to a real section, which is easier for you to pick? Is it easier to pick this one or something in here? It's usually easier to pick the first arrival. The first arrival is the direct right now. Direct is always for the early, I mean, the near offset, it's always the first to arrive. So I cannot use the reflection. They use it in many other cases. If you can pick it, that's fine. However, if you can't do picking for reflected energy, in this case, for example, I'm almost not able to pick it. You always need to pick it for the first for the first trace, the trace which is exactly where the shot is. If there is an offset from shot to receiver, there is an offset. So the equation is not that simple. The equation is not like 2h over v. We'll study this more detail when we talk about reflection technology or technique next slides or next week or next chapter. So reflection is, first of all, is not the first arrival. Another thing, it's not easy to pick it, and usually no one picks a reflection. There is no picking for reflection. We do not pick reflection energy. Another thing, you need to have the source exactly where, the geophone exactly where the source is. This is impossible. There is some distance from source to receiver, always some offset. So for those reasons, are you talking to me?
Yes, doctor. Doctor, I think also because it changed because it is not a straight line. So when you talk
Hi, it's a
two points,
hyperbola.
it will be different.
Yes, it's a
Velocity.
hyperbola actually. It's not a straight line, it's a hyperbola. But it has a velocity. Its equation has a velocity. We'll come back to this because otherwise we'll be wasting our time. We'll come back to this topic, how we can use the reflected energy to do layer, defining how many layers are there and what are the velocities of each layer. Actually, seismic reflection is more powerful than any other technique, like refraction technique or any other technique for imaging the subsurface. Seismic reflection technique is the most common one used in oil industry. 98% the time, what if someone asks you what is the geophysical technique which is used in oil industry, 98% of the time seismic reflection is the one used. They don't use refraction. Refraction have a lot of drawbacks, a lot of caveats. Those are the one we'll be talking about today. On the other hand, the caveats with the reflection technique are much less. It's more powerful actually than the reflection technique. We use the reflection for engineering applications, for site investigations, for many small applications. We even use it to help us for the reflection techniques. So whenever you are doing a reflection technique, sometimes you need some refraction data. So your input might be refraction data. Any other questions related to previous slides before we proceed? Again, anybody missed what I said? I said we'll have the quiz next week. The reason being, I'm having defining the questions in or making the questions in module. That's the reason I was supposed to start by 2:15, but I thought I might be delayed because this problem, and it never been resolved up until probably now, and it might come back. So we'll delay the quiz to next week, the same time. The midterm gonna be on week 8. So it's gonna be on week 8, the midterm, during the lecture time. So let's go back to where we stopped here. Yeah, we stopped here. Caveats. So reflection technique has some problems. These problems should not frighten you using a reflection technique. I have used it many times. I have used it, for example, for a case came from College of Engineering in a court in Abri. You know where Abri is? Abri is a city in Sultanate of Oman. So there is a court, and they came to the queue having an issue. The issue was that water started entering the basement. They have a basement. The first floor is a basement where they keep storing their books, their journals, their papers, all are kept there in the basement. All of a sudden, they realized that water is coming to the basement, and they didn't know what exactly the reason is. So they approached the College of Engineering. College of Engineering came to me asking for any geophysical surveys which can help them. So I have chosen two techniques. One of the technique was seismic refraction. The other technique was resistivity technique. So seismic refraction, the objective was to find what is the thickness and velocity of the first layer. So my objective was to find what is the thickness and velocity of the first layer. In case if the velocity is very low, my conclusion is that the first layer is conglomerate, is very loose material. There is no hard rock. So the water can easily go through this layer. I used resistivity to find out what is the depth to the water. Is there any water there? And yes, I found that there is a huge amount of water. So if I make a drawing, mm, so let's assume that this is the court, and that's the surface of the earth, and this is the basement. So the water start coming to the basement, and they didn't know the reason behind it. So what they did, they asked me to do some seismic or geophysical survey. One of the surveys was seismic refraction. Seismic refraction told me that the depth to bedrock is 11 meter. 11 meter. What's bedrock? Bedrock is a rock with low permeability. That's the bedrock. The water cannot go through this layer very easily. Whereas the rock above the bedrock is loose material, is unconsolidated layer. So that's what I found. And I found that this is not like straight line, whereas it's actually looking something like a zigzag line, an undulated layer. It's going up and down. That's exactly the refraction showed me. And the resistivity showed me that the water is here. The water was beneath. Why were the water was beneath? Because once they experienced that the water is coming inside the basement, they stopped the irrigation. There is an irrigation system. They have a lot of trees on the surface. They keep irrigating them daily basis. It wasn't me who asked them to stop irrigation, but College of Engineering asked them to stop the engineering. I think they approached civil engineering, Department of Civil Engineering. So the water dropped a bit down from that level. You see the agreement, and you see how much they spent compared to what I spent. I spent nothing. So they gave me like for 3 days work. I think it was a bit high price I asked, but I asked for 2,000 Omani riyals. So I said, if you give me 2,000 Omani riyal, I will do the work for 3 days, but in one condition. SQ provides for me accommodation there and provides transportation. So I get a car and I get the accommodation there in Abri. Whereas I spent almost like just 2,000, but they spent 20,000 drilling some holes. And see the agreement between my data and their data. The agreement was like perfect match. Their drilling showed that the bedrock is exactly here. And my seismic refraction technique showed me without drilling anywhere and in larger area that the bedrock is at 11 meters. So this is quite interesting. And I was depending on seismic refraction. Seismic refraction, you cannot say it's useless. It's very useful. And instead of going drilling many wells, each well is almost like 2,000 or 3,000. Better to drill to do seismic surveys. Another case was in Samal. In Samal, you know, the water depth is up to like 150, 180 meters. And to drill that much a well which goes that deep, it's very expensive. You have to pay almost like 5,000, 8,000, or 10,000. It's very deep well. So they approached us. They asked if it's possible to do any geophysical technique. We haven't used seismic refraction, but we used another technique called TDM, or electromagnetic technique. And we suggested for them that there is the oil and go drill. They found where exactly the oil is. So geophysical techniques, they got some ambiguity. But if you analyze them in a good way, you correlate them with the geological thinking, geological observation, what you know about the area, you can come to a good conclusions. So we helped, like we came to conclusion that helped a lot College of Engineering. We helped the guy who approached us for drilling a well in Samal. We helped even, for example, in project we did for Occidental company. Occidental is an oil company. They usually drill very deep wells. They drill up to 3 kilometer, 2 kilometer, but they were trying to get a shallow aquifer, a shallow layer from which they can extract water for treatment. They get water, heat up the water, make it steam, and inject it to the reservoir for ER, enhanced oil recovery. What's enhanced oil recovery? That's a topic in petroleum engineering. Enhanced oil recovery is a technique you use once the pressure in the reservoir depletes. Once the oil will not go by itself to the wellhead. And there is, once you drill a well, you expect the oil will, due to pressure, will go to the wellhead. But at a point, at a stage in the life of the oil field, there is a huge amount of oil, but for some reason, it will not go to the wellhead. It will not be sucked by the well. So you need to use advanced techniques. Those advanced techniques, they are called enhanced oil recovery. So Oxy was trying to find an aquifer, a shallow aquifer, to produce from which water, to get water, treat the water, convert it probably to steam, and inject it back to the reservoir units. Why? Because they want to keep the pressure. So if the pressure is maintained within the reservoir, you can keep producing from the well for very long time. You can expand the lifespan of the field. So what are the caveats of refraction? One of them, it only works whenever there is a velocity increase with layers. So if there is a velocity inversion, a lower velocity below an upper velocity, the seismic refraction will not work. And we already said why is that, because if you go back to the equation of refraction, you'll find that there is a square root. And anything, a minus value below a square root is not a real number. It's an imaginary number. In geophysics, yes, we work with imaginary numbers, but in this case, in this simple case, we don't expect imaginary numbers. We are still within the reign of or regime of real numbers. So that's the reason why refraction technique does not work. Another technique, another problem is whenever the layer thickness is very low, or the velocity of the layer is very low. And as I said previously, we need usually multiple surveys, not simple survey. If the layer is dipping, to determine the true dip, you need to acquire two shots. One is called forward, the other is reverse. To detect the true depth, you need to acquire two perpendicular shots. So what are the normal cases or the problems we have? One of them called hidden layer. The other one is low velocity layer. For the time being, let's talk about low velocity layer because the simplest problem, and how we try to investigate how it happens and how we can tell if there is a low velocity layer or not. It's not easy from geophysical technique, from seismic refraction itself, but you can use then other techniques. Or you can consult geologists. You can ask the geologist. You can go to the outgroup. There is an outgroup. Have you seen the petrol station nearby Al-Khod Sabah? There is a new petrol station and they cut through the rock. Have you seen that place? Here in Al-Khod Sabah, there is a new petrol station. Yes. So there is a petrol. If you go through this cutting, rock cutting, you will find a nice, beautiful geology. The layers are very clear. So one of the things you as a geophysicist or even as a geologist, in case if you have time, you are interested to know how geophysics works, go apply geophysics on top of the mountain and compare your results to the real geology, because you see the outgroup at least up to 20 meters. Compare what you see to the geology, to the geophysics. Geophysics is the results, final results you get. Compare them with the real geology from the outgroup. So here, when I say consult the geology, consult the outgroup, consult log data if you have any well nearby, can tell you if there is a low velocity layer or not, or what type of layers you have. But what happens whenever there is a lower velocity on top of a higher velocity? The ray will deflect toward the normal. And there is never ever a critical angle. No critical angle. The ray will not travel along this line, this interface. So I missed totally this layer. In this T-intercept, this is coming actually from the third layer. This is coming from the third layer, or top of their third layer and the bottom of second layer. It's the same. But the thickness you find from the intercept actually is very well exaggerated. It's the total thickness. Disregarding layer 2. So you will lose this one. Instead of another layer, probably something like that, you missed it layer totally, because refraction cannot map it. And you will exaggerate depth to the third layer, or thickness of the third layer. So you need to consult the geologist. And what are the cases? The cases may be sandstone below shale. Shale layers are of higher velocity. Sedimentary rocks below igneous or metamorphic rocks. Those are the cases. And how you can tell? You can either acquire another geophysical technique or consult a geology. Geologists, as I talked just now, are basically outgroups, geologic map, cross sections, boreholes, logs. Those are the data you can integrate with the geophysical data to identify if there is any scenario where you can expect a low velocity layer on top of high velocity layer. So you will get a hidden layer. Another thing is if the layer thickness is very low. If the layer thickness is low, what happens actually? Let's assume that this is surface of the earth, and this is one of the layers, thin layer. That's the third layer. 1, 2, 3. So the ray goes like that. Let's make this one smaller. Here, ignore this one. It goes like that and still goes like that. The velocity is increasing, layer 1, layer 2, and layer 3. The velocity keep increasing. The normal incident for this one is probably here. However, the energy from deeper layers, the refracted energy from the deeper layers probably arrives first. It arrives before the first layer. Maybe my drawing is not good. So that's one of the cases. So if we compare these two illustrations, the one to the left and the one to the right, let me delete. This one I'm having no problem at all. The first one, I'm getting a refraction from both layers. So this is from first one. This red one will give you this portion, first refracted. Whereas the second one will give you this portion. So this is the critical angle. The head waves start moving up. And you will get a refracted line 2. This is the first crossover, whereas this is the second crossover. This is the critical because here it happens. It's not the first. It's only where refracted energy appears to be recorded. It's not the first to be recorded, but it's being recorded. This is what we call, what angle is that? Or what distance this one is? What distance is that? Critical, yes, critical distance. This is what we call, this is the critical distance, whereas this is the crossover distance. The critical distance for the second layer is here. Here is it. Here it starts appearing. That's its crossover distance. What happens? Let's take the case where the layer 2 is very thin layer. So I start having critical angle at this range or at this value, and the energy start traveling, creating head waves and being recorded by geophones found here probably. Whereas this is the second one, critical angles from the second one, they already keep appearing. So maybe they appear, this one appear before this one. The critical angles from third layer or critical energy from third layer start appearing before critical energy from second layer, because second layer was very thin and the energy went to the third layer very quickly. Third layer is higher velocity, so it start traveling faster. Start traveling faster and appearing before the critical energy from the second layer. And I missed it. I missed the critical. So it's happening. It's this one. It's being recorded by geophones. Geophones getting the energy. However, they are not the first. What is the first? At this far distance or far offset, actually second critical angle. The second critical angle is the critical angle from this layer. This is from which layer? This layer. That's the thing you will find. So you as a geophysicist, you whenever you are dealing with refraction energy, you think it's always the first to arrive after the critical. Before that, that's the direct. Before the crossover, sorry, before the crossover distance, that's the direct. You don't care about later arrivals. You assume the later arrivals are all reflected or noises or surface waves like ground rule. Ground rule is a terminology used, if I go back to some figures, because you will hear this ground rule quite often. So these are ground rules. And what are ground rules? If I talk about ground rules basically are surface waves. These are ground rules. So this is, I believe, very clear when we have hidden layers. One of the cases is low velocity. The other case, whenever you have very low thickness layer, a layer with low thickness. Another case, when I probably miss some layers, is not related to the geology, but it's related to your acquisition system. You will not be sampling every layer. So let's take some cases. Let's take two cases actually. What are these? Who can tell me what are these dots? What are the dots you find in this figure? A. Yeah, they are kind of a station, but those stations are geophones, yes. So this is a geophone here, another geophone here at this distance. This is where the source is. This is the geophone and so on. So the trace goes like that. And suddenly when start receiving energy, in this case is the direct energy, start moving, making some disturbances and so on. So this is also a geophone somewhere here. This is my shot. This is the location of the geophone. The energy takes long time. So in this case, the first arrival energy is not the direct. It's not this ray. Whereas probably someone from deep. So how many lines I'm getting? How many straight lines? This is direct. This is one. This is a second one. This is a third one. And that's true. 1, 2, 3. 1, 2, 3. And that's the 4. This is the first one, second, 3, 4. But the refraction, 1 refraction, 2 refraction, 3 refraction, which are 1, 2, 3. This is coming from the direct, from the top. if I delete the line, I'm seeing these things as imaginary things, not real things. These are imaginary things. I missed one of the layers. I'm not seeing one of the layers. Which layer? I missed this layer. I missed this layer. So I'm seeing one layer, two layer, three layer. Whereas the real one are more than three layers. What I should do, what I can do to bring all the layers? Who can tell me? I'm missing one layer. This one is getting the line from this one. That's true. This is fine. The last one is fine. Whereas this line is totally missed. Something like that. Which is has been missed. I couldn't map it. I couldn't map this line. There is no problem with the geology. Geology is fine. The velocity is increasing. The layers are thick too. There is another problem. The problem is with the acquisition system. So who can tell me how I can resolve this problem? We have studied that. Yes, that's true. We need to make the geophone spacing, we make it smaller. We make more geophones, bring more geophones, so we can detect it. Because we are just connecting these lines. If we have more dots, we might get more lines. So this is something you can do during the field acquisition to better image the subsurface. And we talked about that during our introduction part. This is a real case where you miss some geology or some valuable information from the subsurface because you haven't sampled the geology properly. Your geophone spacing is high, so some layers were missed. In this case, I have very large. One geophone is here, the other one is here, the third one somewhere here, and so on. The last two, one of them probably here, and this is the last one. So I'm having only 5 geophones. And how many layers I'm getting? I'm getting the first, direct, and the last, which is this one, the highest velocity. I missed these 2 layers. These layers, 2 layers were not mapped. The reason being because my geophone sampling, my geophone spatial sampling is not appropriate to image the subsurface properly. When I talk about spatial sampling, there are 2 things you take into considerations. Sampling in general. One is temporal sampling. The other one is spatial. Spatial is in terms of space. Partial sampling. In geophysics, this is just partial sampling, but there is a temporal sampling. What is temporal sampling in geophysics? This is apart from our slides. Whenever you have, for example, some data, the data usually they are continuous data. The data you record are initially continuous data, but our computers cannot record continuous data. Our computers, let me ask you, how many real numbers are there between 1 and 2 or 0 and 1? How many real numbers between 0 and 1? 0 and 1. How many numbers are there? Real numbers. Infinity. How you got that sign? Yeah, infinity. Infinite numbers. Computers are limited in terms of size. Oh, really? Yes. That's really super fine. So computers cannot, you know that, they cannot store infinite numbers, infinite data. They have limitation in terms of space. So to overcome this limitation, you need to sample your data. You record, even though your geophone is shaking continuously, you take the shaking at specific times. And that's what we call temporal resolution or temporal sampling. What you see here is spatial sampling on the surface. The recording, how you record your data, they also affect how you resolve the subsurface. So one of the scenarios you might find, have you ever watched a fan moving? Have you ever wondered while sleeping in a room and watching to your fan at the ceiling? I think many of you did this. A phenomenon you will notice that every night. Yes, a phenomenon you will notice that the fan probably is moving in the other direction. Your imagination tells you, oh, I think it's moving in the opposite direction. And this is actually something we called uh, aliasing. We call it aliasing in geophysics. What's aliasing? You haven't sampled, haven't temporal sampling. Your eye is not strong enough to take a lot of screenshots. The fan is moving faster than your mind can sample, can take snapshots. Yeah, it's very high speed, but your eye cannot track with the high speed of the fan. So your eye think it's moving in the other direction. So if it's high frequency, it's a trace of high frequency. If you not sample it enough, you will destroy the frequency. If you not took enough samples, you will destroy it. Something like what you say, yani, let's assume this is my analog continuous data. I take two samples, one here, and three samples. This is my original. And in computer, you take sample here, and computer, what it does, it just continue them like that. So you destroyed your original data. You destroyed your original data. And that's exactly sometimes what happened with radio signal. I'm not sure whether you have experienced this or not. Radio signals are very low frequency signals moving in the air, coming to your car station. Sometimes when the sky is nice, the weather is good, you will tune your radio, you get the signal. But even if you tune it right and the weather is bad, the weather is destroying the signal. The signal is moving to a different signal. You find two channels, even though they are supposed to be of different frequencies, they're interfering together. You change the frequency, you're receiving the same frequency, but it has been changed because of the bad weather. In geophysics, what we are interested in something spatial sampling, and the other one is temporal sampling. How we detect offset? How we detect that there is a fault in the subsurface? What happens? How refraction techniques works? A reflection technique is the best. to detect reflection, not refraction, but we'll come back to this topic later on. What happens whenever there is a reflection? You'll find that there are two different segments of the same slope. Why same slope? Because their velocity is the same. We take this case whenever the second layer is horizontal, as you find here. If it's not horizontal, this is not possible. So in a horizontal layer, if there is an offset in geology is represented as a fault or a fracture. A fault or a fracture. Some fractures can be big fractures. Some fractures have displacement, some does not have displacement. Some fractures can have displacement, some fracture have only opening. It's a fracture that happened or closed. So how you see them? It happens that the energy is traveling in every direction. And some of the energy will travel, hit this layer, go in the lower layer with higher velocity. Since it's traveling in every direction, sometime it will hit this corner. Since this corner is what is a corner, is not smooth line, it creates diffraction. We'll talk about diffraction later on next. It also creates a refracted energy. It will create refracted energy, which creates in-tone wavelets following Huygens principle. And I find two different layers. So these two, they have some offsets, but their slope is the same. They are parallel to each other. They are parallel to each other. You can tell then there is an offset in the layer. There is a fault cutting through the second layer. If it's cutting on the surface, you will find a fault scarp. That's a fault scarp. If you are on the surface, this area is called fault scarp. So on the outcrops, you'll find these things, but in the subsurface, because we are not seeing what's going on with the geology, seismic can help you to find out the faults. So what's good about this? You can project these lines, get the t-intercept for both lines. Each one gives you a thickness. Each one will give you a thickness. So the difference between these two thicknesses, this is first thickness, this is the second thickness. The difference between these two thicknesses gives you a value. That value is what?
Time intercept.
No, the difference between the thickness of this layer and that, so thickness of the layer obtained from this intercept and the thickness of the layer obtained from the other thickness, the fault height, thickness of the fault. Yes, so this is the value. So any fault usually it has two values. So if you talk about fault, this is a fault. Fault have this value, straight line. This is one thing, and this is another thing. This is called heave. Heave. This is called throw. This is called throw, whereas this thing, this from here to here is heave. This is throw. So what you obtain from these two intercepts, intercept 1, intercept 2, you get two values, two different heights, or thicknesses. This thickness H2 minus H1 gives you the throw of the fault, which is this value. Whereas this is the heave. This is heave, this is throw. Is that clear? How you can tell if there is a velocity change laterally? How you can tell you do something called fan shooting? You do something called fan shooting. It's sort of tomography. So what you basically do, let's assume that this is the rock, a different rock than the other rock, which is the host rock. That's the host rock. And it has been interpreted or cut through by some dike or some magma or some other thing, or maybe salt. This is salt. And you try to find where exactly it is on the surface. It's يعني area on the subsurface, not on the surface, but on the subsurface, but how much it is big. You do fan shooting. What's fan shooting? You have the source and you have one receivers or many receivers. In this case, we have one receiver, and you keep recording the time. And you expect that there is some refraction too. So this is the refraction. And this is where what we call head waves. What happens here? Because if we assume the velocity with this layer is higher, velocity of this intrusion is higher than the velocity of the host rock. What happens to the time of arrival of, let's assume, 1, 4, 5, 6? What is the time of arrival for this, for the refracted energy? Refracted energy at these 4 or 3 geophones. Is it higher or lower? Time of perfect. That's true, Abdulaziz. Lower, yeah, because this is higher velocity, takes least time. So what you say that here I have something different between this thing. Not exactly where, but at this area. You do the same using another shot. We cannot record the slope, Abdulaziz, because we have only one geophone. You get one time. First arrival. We assume that the first arrival is the refraction from first layer. Is that clear, Abdulaziz? Yeah, because there is one geophone, so how you can draw a line? A curve or slope? No, you can't. What you do, you take another shot and just make one geophone. You don't waste too much energy and start again. These 3 gave you this zone. These 3 from the previous shot gave you these zones. And now from shot 2, you will find this zone. Oh, this is almost touching it. So the shaded area between these 2 is some ambiguous area. It's some anomalous area. Some area where the area or the velocity is different. the velocity is higher. That's what we call fan shooting. And this is some sort of tomography. And what exactly is tomography? Tomography can be explained using this video. I explained this video back ago but let me try to play this one. Okay, let me save it. General Geophysics slides. Oh, it's saving as picture. Seismic tomography. I think that's the one. Let me bring it here. And I will play it for you soon. Do you see it?
CAT scans produce 3D images of the inside of the human body. The instrument uses an energy source that emits a fan-shaped beam of X-rays and a receiver or X-ray detector on the exit side of the patient that records a snapshot X-ray. Multiple snapshots, collected during one complete rotation, are sent to a computer to create a cross-sectional image or slice of the body. Between rotations, the body is moved through the machine in increments with an image slice being computed at each position. Every rotation, here speeded up, yields an image of a new slice as it moves through the length of the target, in this case through the head of the person who is lying in the chamber. How simple seismology would be if we could do a CAT scan of our planet, but X-rays cannot penetrate the Earth. So how do we know what's inside? By using seismometers as receivers and earthquakes as the energy source, seismologists look at the Earth in a similar fashion. By using the arrival times from worldwide earthquakes, seismologists were able to define layers in the Earth. Later, they expanded the method to look at smaller areas. Let's look at how this is done by using a highly simplified model of a uniform crust. For simplicity, we will use straight line ray paths so the seismic waves won't get deflected and bent by different layers as they do in reality. An evenly spaced grid of seismometers records earthquake arrival times. Seismic waves travel through different materials at different speeds. By measuring the time it takes seismic waves to travel from an earthquake to different seismic stations, scientists deduce velocity variations within the Earth. Late arrival times for the slower ray paths in the shaded red area indicate slowing has occurred somewhere along the way. We won't actually know where the slowing has occurred until the data have been analyzed. By using what we know about how seismic waves travel through different materials, we can infer what the structure might look like. What does this tell us geologically? What are these anomalies? Well, they could be regions that have different compositions, temperatures, or fluid contents, including water, steam, or magma. In order to know which, seismologists work with other Earth scientists such as geologists and geochemists to combine independent observation to solve ambiguities.
I hope this is very clear. So this is how tomography works. Tomography works by sending seismic energy from every direction, from all possible direction, and finding some ambiguity or anomalies within some of the recording. So since you are recorded many from using many geophones, you can infer places where there is some anomalous readings. So let's move to something called ray tracing. What is ray tracing? Ray tracing is using computers and your knowledge of physics and seismology. In this simple case, in this case of refraction, what is the governing equation? What's the equation we use to tell how waves refracts and reflects? Who knows? Guys, are you serious? What's the equation which can governs, which is the governing equation decides how waves travels in the subsurface? Snell's.
Snell's law.
Yes, that's true. So Snell's law, that's the law which governs how waves refract or reflect in the subsurface. If you know how to use this equation, what I can do, I can, for example, uh, draw a simple model, computer model, not real model, and say this one have velocity of that much, 2000, and this one has velocity of 3000, and simulate, make a model, say that there is a source, and there are 3 geophones or 4 or 5 or whatever. Using computers, using your knowledge, or using hand drawing. And if you can do it by hand, it's fine. So let's say how energy will travel and refract. Refract. So let's simulate. First of all, this is 3000. We can tell from incident angle, if we know the incident angle as is somewhere here, what is the critical angle? If you know this one, the velocity of the both layers, you can tell what's the critical angle. At what angle refraction start appearing. So you simulate it. You tell the layers how they move in the subsurface. Not in real, but this is some simulation because you know Snell's law. You know how the wave refraction happens. What's the governing equation? And if I know it, I can tell at what space, at what time, because I know this equation. I know what equation, this equation. So now I know the velocity, I know the thickness, I drawed my model, and I can tell at specific geophone, which is X, what is the travel time of refraction. So I can tell what is the travel time of refraction. This is what I call an initial guess. I made a guess of my subsurface. I made an image, not a real one, a model, and from Snell's law, equation of Snell's law, I calculated travel times using Snell's law and the equation I just showed to you. However, you have a real Earth, real observation you made somewhere. In that real observations, you are not sure what's the velocity of the Earth and what is the thickness of the layers. In the real observations, you only got data. So in one hand, you have the data alone, but no model. It's the real data you acquired from the field from somewhere. In the other hand, in the opposite direction or opposite contrary, you have what? You have a model from which you use the model, a guessed model, not a real model, a guessed model you created some data, we call them synthetic data. You match them, try to compare them. These data are from the field, whereas these data are synthetic data from a guessed, an imaginary model. If they are not matching, what do you think of your model? Is it similar to the real geology? If these two data are not matching, the synthetic and the real data, what you can tell about your model? Is it similar to the real geology or not? Who can tell? No, no, not accurate. Your model, you guessed, is not similar to the real geology. The geophysics, by the way, most geophysics are working right now using this technique. They are creating a model and they know how physics works, how Snell's laws travel, how waves diffraction happens, what's the governing equation, and let the computer do it. Or they don't want to do it by hand because cumbersome. But computers can do it. Excel can do it, for example. In Excel, you say, okay, this is my layer, and layer one, what's the TX, what is the distance, what is the time? You draw some lines then. You draw some lines using Excel. Compare this one with the real geology. With the real data you got from the real geology. Compare the synthetic. If they are not matching, what you do, you change your model. You change the velocities or you change the thickness. Try again. Till there is a match. This is a trial and error. So you change your model, the one you create, until your data is matching your observed real. Your synthetic is matching or with very small error. It cannot match perfectly, never ever, but at least the error is bearable. It's sensible. It's possible to have some small error because of some noises. The data were in the real data are having some noises, but in your model you don't have noise. Maybe some whenever they were acquiring in the real field, whenever you were acquiring the data, there were some noises, some car moving along where the refraction line is, was creating noises. And by the way, all geophysical technique are like that. And geophysics technique in general works like guessing a model, doing synthetic or forward modeling here, and changing your model till the observed and real, the observed and synthetic are matching. To simplify this changing process, they created something called inversion. So instead me doing it, I let computer do it, but will not go deep into this point. And this can be done through ray tracing. So Snell's law tells you where the ray goes, where it went. So if you know the time, you can tell its path. If you know time, at what time the energy arrived, you can at least guess where exactly it passed through, which layer it went. And this is what we call ray trace. We trace the ray path. And through ray tracing work, we can then make a model which is representative of the real year. Is that clear? I'm sure if you read this by yourself alone, you might not understand a bit of what's saying even in the book. So this is what we say about forward and inverse modeling. So we guess an initial model, see what the data, synthetic data, it brings to us, compare it with the real data we observed from the field. If there is a match, good match, that's fine. We accept our model. If there is not a match between them, we change the model. See the change or what our change reflects to the synthetic data. Compare again, and it's an iterative process. What I mean by iteration, it's a repetitive process. You keep iterating, one iteration, second iteration, third iteration, until the error changes to the minimum. So you might go wrong. You might change it and the error becomes larger. So if you go in this direction, change or increase the error, you are doing something wrong. Let's talk about survey. How seismic surveys work. What is usually the source in seismic refraction survey? What the refraction, what the source we use? What's the type of source? Guys, it's a hammer. Hammer, yes. We use a hammer as a source. So a hammerhead cannot penetrate. The energy released by hammerhead can go up to 50 meters. And hammer has a switch. So comparing the earthquake energy to hammerhead, and you during the last lab, you were asked to know what is the origin time. Am I right? You were asked as a company or a question in the lab, what's the origin time? Because I'm in the case of earthquake, I'm receiving the energy, but does not know the exact time the earthquake happened. Here, I start the recording exactly the time I hit the plate. There is a trigger system or impact switch, they call it. Whenever I hit it, it sends a hit and it sends the signal to the recording equipment. Oh, hammer have been hit, start recording. So it start recording the energy which is received by geophones. The simplest is having one geophone, but usually we can have more than one geophone. So there might be some noises. The noise can come from wind, cars. So to minimize the noise, we can deploy the survey during a quiet time, or another thing we can do to minimize the noise is, who can tell me? Let me ask some questions. Who can tell me how we can minimize the noise, at least for the hammer?
By repetition.
Yes, by repetition, by repeating, by hitting again and again and again. Since the noise is a random thing, whereas the earth is a coherent, the signal coming from the earth is coherent, it add up coherently or constructively, whereas the noise will add up destructively. But there is a limit. After that limit, after probably 15 shot, you will not observe any change, any improvement in your signal. So it's better to stop repeating again or exhausting your energy, doing no improvement to the signal. We do this all the time. Whenever we do, for example, as field in the earthquake in our department using our system, we do 5 shots, 7 or 15, or make it open. Sometimes we make it open. The systems allow that. You can set up this in the system. You can tell the system, I want 5 shots, I want 7 shots, or I want unlimited number of shots. If you make it unlimited, you keep observing and observing until a point you say just stop. That's my end. So what is the depth you are targeting? So again, as some of you said, stacking is a good thing. Stacking is repeating the signal, yani, improve the signal. But the depth you want to go is dependent on the survey. So how is that? So let's say I want to penetrate or investigate a depth of 5 meters. What is my spread length? What's spread length? This is spread length. So usually what do you have? You have a source. This is your source. And you have multiple geophones, 1, 2, 3, 4, and so on. Up to, in our case, we have from 1 to 24. And the geophone spacing from one geophone to another geophone is geophone interval. We call it geophone interval. So maximum geophone interval in our system at our department is 5 meters. So if you have 24 geophones and the spacing from one geophone to another geophone, what's the total length from, what is the total distance from first geophone to the last geophone? If I have 24 geophones and the spacing from one geophone to another geophone is 5 meters, what is the total length? Is yeah, -1. 24 24 minus 1 times 5. So let's assume this is, I have how many fingers? 5 fingers. Let's say the spacing from one finger to another finger is 5 meters. So what is the total length? 5, 5, 5, 5. How much? Is 5 times 5? 20. Yes, it's not 25. It's 5 times 4. So don't make this mistake. The 24 minus 1 times 1. So this spread length, how much is the spread length defines for you how deep you can go. So 24 to 115 meters for our case divided by 10 gives you the thickness. Maybe 15 meters or 12 meters. You cannot penetrate deeper than that. You cannot go deeper than that. So geophone array should be about 10 times the depth to the interface. This is the geophone array. From 1 to 24, the distance is the geophone array. So as I said, hammer cannot go very deep. Hammerhead, the energy is being dissipated for two reasons. One of them is intrinsic, we call it intrinsic attenuation, energy attenuation, because the energy, some part of the energy is being transferred to heat. If I hit the hammer, one of them, the energy is being dissipated. The other one is energy traveling in this larger area. Two things. One is energy is being dissipated because some part of it being lost as energy. The other thing is because it's traveling larger area. We call the first one in geophysics, at least geophysical terms, spherical divergence, spherical because you're traveling bigger distance. The other one is attenuation, spheric or attenuation in general, the energy being attenuated. So the maximum depth for hammer and 24 geophone is almost like 15, 12 meters. So how we can compare them? What we get finally from, what are the things we obtain from seismic refraction? We obtain two things, as we already know. One of them is the thicknesses of the layers. The other one is the velocities of the layers. So again, back to the first slide. If you do survey, a geophysical survey, and let's assume you did a refraction survey and you got or obtained a depth of 50 meters. One of the layers is 50 meters. And you know from the acquisition specification that you were using a hammer and the spread length was let's say 150 meters. You cannot expect a depth of 50. In that case, you probably did something wrong in your calculation, in your analysis, not in the survey, but during the process of converting your data to geology, to geological parameters, which are depth and velocity. So velocity, once you get it, you compare it with geological rocks. The rock, you know. The rock, each rock has its own velocity. Usually, the harder the rock, the higher the velocity. The denser the rock, the higher the rock. So temperature, The higher the temperature, the higher the velocity. Higher the temperature, higher the velocity. Unless we reach something called Curie temperature, but don't go beyond this point. What's Curie temperature? Curie temperature is the temperature at that point the rock or something converts to liquid. Part of it goes to liquid, start melting. So anhydrite, we have sedimentary rocks. You see, this is the range of velocities. Sandstone has a high range of velocities. This is kilometer per second. What's the velocity of air? Velocity of seismic waves in air is, as we say, 300 meter per second. Velocity of water is 1.4 to 1.5. Ice is higher. Velocity of natural gas is quite low. So you can easily sometimes tell from seismic sections that there is hydrocarbon or no. The velocity changes a lot. And if there is, especially if there is gas above oil or above water. Gas has very low seismic velocities, either P or S. Right now we are considering only P wave. This is P wave. So S wave is lower usually than the P wave. So whenever you get high velocity, like above 5,000, these are like usually metamorphic or igneous rocks. It's not one number. It's not one single number. It has a range usually. So this range is dependent on many other factors. Some of the factors I can name: saturation, water saturation, porosity, age of the rock, temperature of the rock, depth of the rock. One of the characteristic of shale is that seismic velocities will increase the deeper the shale is. Shale is an incompetent layer, yani you can squeeze it. That's the reason it's usually a source rock. So shale is a source rock. Why is that? Because if it goes deeper, even though it's not permeable, it's impermeable, it does not have a lot of porosity or permeability, the shale rock. If you squeeze it, if you bring it deeper, the hydrocarbon can escape, that can go away. It's incompetent layer, and it's squishy layer, can be reshaped. The deeper it goes, the higher its velocity becomes harder and thicker and denser and more massive. That's some of the characteristics of the shale rocks. So porosity affects a lot even sandstone rocks. Sandstone, you see, starting from 2,000 up to 5,000. The reason being why we have variation in velocity for many reasons, as I already said. Clay, dry, unsaturated, saturated, unconsolidated layers, they are of very low velocity. These are unconsolidated sediments. Whenever you obtain your velocity model, compare them to what you think they are. Their geological counterparts using such a table. So I stop here for any questions you have, to receive questions from your sides, anything you find not clear. We'll have our quiz next week. Unfortunately, I'm having problems with every time saying that there is a security problem. It sometimes goes, sometimes get back. Maybe the question I was writing is not easy question. There was no figures. Some of the questions, they have figures, some figures. So whatever I change with them, I lose connection with the module. it just crashes, and I get this warning message saying that there is a security problem. I need to contact them. It was happening even last week, I believe, week 5. So do you have any questions? If you do not have questions, I will close. No questions, guys? Stop recording.